So we've almost finished with this part of the network, but the last thing I need to do is lay down a couple of nodes which will allow us to extract and save out to disk the point clouds that we're going to need when we render. And the effect that we saw of the white blobs appearing where the spheres hit the ground is achieved by using a shader which is loading in point cloud information. And the information it's loading in is going to be the positions of the particles which have already hit the ground. So let's Control C, Control V to copy the blast node, and then I'm going to delete non-selected. So this is going to leave me with just the points that have hit the ground, and then I'm going to append a null which will allow us to reference this easily, and I'm going to call it out hit particles. So how do I go about saving out a point cloud with the point data that we have here? Well, the answer is I need to go into my out network, and I need to lay down a geometry ROP, and I'm going to refer it to the out hit particles null that we just created. And by default, a geometry ROP like this saves out the data in the BGO format, and that's not really what we want. What I want to do is save it out in the point cloud format. I'm going to save it in the geo subdirectory, and in fact I've already rendered out a set of point clouds, but if we use the format PC, that will ensure that our point cloud is in the right format. So when I render this, it's going to render out a point cloud for each frame with the data about the points that have hit the floor for that frame. So I'm going to do that and then pause the video. So I've renamed the node right out point cloud, and I've given it a range of 1 to 100, and I've rendered it. And we can examine what's in those point cloud files that we've just written out by using a geometry node, and I'm going to call this visualize point cloud. And if we dive inside, we've already got a file node here, and I can use that to load in the point cloud data. And we can see that we've pretty much got all of the information that was in the points earlier on. There's one thing to note. These are attributes. We would call these attributes when we're looking at them in the SOP context. When you're reading in a point cloud, these are called channels. For example, this data here would be the P channel, this would be a channel called V, Accel, and so on. Now in fact, we're not going to use anything like all of these attributes, so we could have deleted the attributes using an attribute SOP before we rendered them out to file. But there we are. So the next step is to create a shader that can use the point cloud data. We move on to developing our shader. Just one remark about point clouds. All that generally happens is that the geometry node, geometry output node here, writes out exactly the data that it finds. You can ensure, and indeed it's often wise to ensure, that the point cloud data is transformed into world space. You can create some pretty subtle errors if here at the object level we'd been using an object level transform on the falling spheres geometry, and we wrote out a point cloud, that might confuse our shader. So it's always a good idea to enable the world space transformation on your output ROP. So let's go into a shop context, and I'm going to just use a basic material as the basis for the material we're going to use to shade the surface of our terrain, of our floor. Let's enlarge this and dive inside. And we have a pretty complicated network here, but in fact all I need to do is pick up the point cloud and decide how close we are to the nearest point. Based on that, either make the color to be white or make it the color that's being calculated by the rest of the shader. So we're going to end up with a color mix here, which will just mix the color which is being created by all of this network here with the color that we're creating here if we're near a point. So how do we start using a point cloud? Well, you need to open a point cloud before you use it. So we need a PC open node. But in some circumstances you get a huge number of points within the given radius. So it's often a good idea, if not for any other reason than for efficiency, to put a cap on the number of points that the PC open is going to collect. And this is where the max points parameter comes in. This allows you to set an upper cap on the number of points that are going to be considered. The cone and preload parameters are used for matching when you're using normals. The cone parameter is used to match when you're using normals. We're not using that today, so I'm not going to go into it. The preload simply determines whether or not the point cloud is loaded into memory during the shading operation or is retained on disk and accessed as necessary, and you in general want to set that depending on how big your point cloud is. What this does is return a handle rather than the group of points itself, but the handle will allow you to access the points that this PC open has returned. So just to recap, the naming of PC open is slightly misleading. This is not opening the whole point cloud. What it's doing is looking inside the given point cloud file and finding the points which are near enough to the point that we're currently shading to be interesting to us. I'm going to pause the video and create some of the inputs that we're going to need in order to use the PC open. So what I've done now is attach a parameter which will give us the file name, attach a max radius parameter which will give us the search radius, and in fact it's also going to be the radius of the white blobs that we're going to see reflected on the floor, and I multiply that by a constant 1.5 just to make sure that there are no mathematical errors and that we don't miss out points in this point cloud that we might otherwise want to look at. And then I bring in the global position variable and I transform it from the current space or coordinate system into world space and then feed it into the position here. And that's very important because if you remember, we wrote out our point cloud in world space, and by default the shader is operating in camera space, so you need to make this transformation, otherwise things won't work. So what we're getting here is a handle which is going to allow us to access those points which are close enough to the point we're shading to be of interest. So we may have, say, 20 points. And what we want to do in this case is iterate through each of those points and make a calculation based on how close we are to that point about whether or not we're within one of those white blobs that we want to place on the floor. Before I go into implementing that, I just want to mention a much simpler technique which you can often use with a point cloud, which is to use the point cloud filter node. And a point cloud filter is very simple. What it does is take a handle, and it takes the name of a channel, You wouldn't normally want to use the P channel, and it returns the average value of the points of that attribute, of that channel, for the points that we've collected here. So if you wanted just to see what the value of X was in the points that are near to the point we're shading, use the PC filter node because it's much easier. But we're not going to be able to do that. We're going to need to use a while loop to iterate through each of our points. And we need to drive our while loop a condition that is going to evaluate true while there are still points in the collection that the PC Open is giving us. And the expression that we use for that is the point cloud iterate expression. And we feed in a handle, and it gives us a Boolean value of whether or not there are any more points left in the point cloud collection that we've got out of our PC Open. I'm going to need a few more parameters going into this while loop, so I'm going to pause the video and I'm going to set those up, and then we'll have a look at what we need to put inside the while loop. So what I've set up here is a while loop which has the condition. I'm then feeding in the transformed position of the point we're currently shading. I'm feeding in the max radius parameter. I'm feeding in the handle from the PC Open, and I'm feeding in a constant. In fact, it's not a constant, it's a variable that we're going to use to store the amount of color, if you like, that we're picking up from the point cloud, from those points which have landed on the floor and are stuck there. So let's now have a look inside the while loop. And the while loop has an input which allows us to access those things that we've fed in to the higher level node, and it has an output which allows us to feed things out of the while loop. And the first thing that we should always do is ensure that we're not going to create an infinite loop. So I'm going to put down a PC iterate node and attach the handle to it. And that's going to ensure that this only loops as many times as there are points in our collection of points, because the PC iterate only evaluates to true while there are still points to look at. The next thing I'm going to do is draw in the position of the point, the current point we're looking at. Remember, we're inside a loop here, so we're dealing with a single point out of that collection that the PC Open has given us. And I'm going to extract the value of one of the channels of that point cloud. And what I'm going to do is have a look at the P channel, the position channel. So this is going to give me the position of the current point in the point cloud that we're looking at. And the next thing I want to do is compare that to the point that we're currently shading. And I'm going to subtract one from the other. So I'm going to take the position of the current point in the point cloud, I'm going to subtract the current position in world space, and then that gives me a vector which I'm going to take the length of. So what we've got now is the distance between the point we're shading and the current point in the point cloud. And what I then want to do is vary the amount of color that we add depending on how far away we are from this point. So what I'm going to do is use a smooth function, and the amount is going to be the length, and the minimum is going to be 0, and the maximum is going to be our maximum radius. And what the smooth node does is produce a smooth ascent from 0, when this amount is equal to the minimum, is equal to 0, to 1 at the maximum. So this is going to give a value of 0 to 1. If we're really close to a point in the point cloud, it's going to give you a value of 0. And if we're further than a distance of max radius away, it's going to give us a value of 1. And of course that's the reverse of what we actually want. We want there to be colour when we're close to one of the points, and we want there to be no colour when we're further away. So I'm going to take the complement of that, and then I'm going to add this to the existing value of our constant. And then I'm going to feed that back in to the constant. So what's going to happen here is that with each iteration, the value that we're deriving from how close we are to the point in the point cloud is going to be added to any other accumulated value that we've got in that constant. So what we're going to end up with is a total for the amount of colour, if you like, that we're gathering from the points that we're near. But unfortunately, point clouds are not completely straightforward when we are using VOPs. That is a node-based creation of shader, such as we're doing here, because the while loop relies on recalculating a value at each iteration of the loop. So it's going to use this PC iterate to determine whether it needs to loop again. But in fact, PC iterate has a subtle further function. Because you may ask, well, here we are, we're extracting the position value of the current point in the point cloud, but how do we know which the current point is? How do we know when to move on to the next point and have a look at the next point? Well, the answer is that internally, every time you call PC iterate, it moves the pointer, if you like, an internal pointer, and says we're moving to the next point in the point cloud. So every time you call PC iterate, you're moving on through the point cloud, and you'll get potentially a different value when you use a point cloud import. Now, this is important because as we reach the end of our point cloud, when we're on the last point, we want to make sure that we extract this position information before we call PC iterate. If this network is evaluated in a way which calls PC iterate first, and then uses the point cloud import to get the data, the PC iterate is going to move the internal pointer beyond the end of that collection of points. It's going to point to rubbish data that doesn't mean anything, because we will have gone beyond the limit of the number of points that we've got in our collection, and then we're going to try and access data from that place. And that's going to create some nasty, subtle errors. And the problem with VOPs, rather than coding this in VEX code itself, where it's fairly straightforward, is that you can't easily control the order in which these are evaluated. And indeed, if I right-click on this and say View VEX code, and we have a look right at the bottom, we should see that at some point, if we can find it, that I think this is it here. Here we are. This is our while loop. This is the code being produced by these nodes. This is the VEX code being produced by these nodes. And as we can see, we've got a while loop that's based on the value of condition, and condition is in fact going to be based on PC iterate value. Can't see that just at the moment. There we go. So PC iterate, that's the initial PC iterate that we do before entering the while loop. The value of that is put into the variable success. Then in the while loop, It's based on condition. Condition is set to the value of success here. But then, the first thing that we get in our while loop is setting a value of success1 equals PC iterate, and then we're getting the PC import. So what's going to happen is at the last point in the point cloud that we're interested in, this is going to produce a subtle error. So we need to cheat. We need to cheat in order to ensure that this PC iterate happens as the last thing in our while loop rather than the first. And the only way we can do that is to introduce some dummy nodes. And one of the things we can do is use a switch node, and we can switch between the value of handle and the sum of our, let's just feed that in, between the value of the handle and the sum coming out of our addition here. And then I can feed the result into there. And that should ensure, if we ensure that this switch is, I've attached this to the wrong thing. The switcher index needs to be 0. The 0th input needs to be the handle, which we actually want to use, and then we put a second input into input 2. Now in fact, because the switcher index is always 0, it's always going to take this value here, which is the handle, which is what we want, and feed that into the PC iterate. However, because we've got this connection to the add node, this is going to be evaluated after the add node, and thus the PC iterate is going to be evaluated after the add node. It's going to do exactly the same thing as it was doing earlier, but it's going to be evaluated in a different place, and if we view our VEX code, we can see that it is now the last thing that happens in our VEX code, and it happens after the PC import, which is now the first thing in our while loop. So that will solve a rather nasty, subtle bug. Okay, well, I've rounded off this shader, and I've done that by putting in a color mix node here, which takes the color from the basic shader, and a parameter here which is the point color, and it mixes them together based on what comes out of the while loop. And I've corrected one error in the while loop. The PC import node here was in fact connected to the condition. It should have been connected, of course, to the handle. So what we should find now is, if we go up and promote material parameters, we end up with, and I've also done this, which is arrange the parameters so that they fit into a tab here, that we get to choose the point cloud texture, and I've set that already to the textures we wrote out earlier, the point cloud files we wrote out earlier. We get to set the maximum radius of the blobs, and we get to set the color of the blobs. And I've also made the base color of this shader red so that we can distinguish it easily from where the points are. So I need to assign that to the ground. And the other thing that I've done here is add a mantra node, which should mean that we can render this straight away. But in fact, before we do that, just to make sure that it's working properly, I'm going to go into our object and look at the falling spheres, and I'm going to disable blast here so that we will see spheres rendered when they've hit the ground. And the reason I'm doing that is that will enable us to check whether or not we're getting a blob at each of the sphere positions. So let's render that. And here we are. And we can see that at each of the spheres that's landing on the ground is creating a blob on the ground created by that shader that we've just written. Let's just view that without the blast disabled. And there we are. So that's an example of how to use a point cloud in a shader in Houdini.